Dr. Ludmila Kuberkova from the Institute of Physical Chemistry in Prague, and myself from the University of Milan. So the plenary lecture of this afternoon is by Professor Ichikawa from the Catalytic Research Center of Kaido University. Professor Ichikawa, I think, is well known for the people that are working in catalysis, and his lecture is on oxygenate intermediates in CO hydrogenation by two-side CO activation of bimetallic cluster catalyst.
Thank you, Chairman. I would like to express the hearty thanks for particularly Professor Sorinosi, how nicely organized this symposium. I would like to propose some ideas of two-side CO activation governed by the adjacent heterometals active sites involving the oxygenate production in the CO hydrogenation. I appreciate some preview by the Professor Kunitsinga in this morning session. I would like to add some more the flavors of the backgrounds of this subject. The carbon monoxide is activated by the different CO chemsorption mode on the metal surface, which reflected in the CO hydrogenation to provide the different product selectivities. In this sense, the transition metals could be classified into the three groups. First is the Fischer-Tropsch metals, such as iron, ruthenium, osmium, cobalt, nickel, which easily dissociate carbon monoxide into the carbonic carbon and oxygen on the fresh surface. The carbonic carbon is subsequently hydrogenated into the methane and hydrocarbons, and oxygen converted into water. By contrast, the noble metals, including copper, absorb carbon monoxide non-dissociatively in keeping the carbon-oxygen bond, which is specifically hydrogenated to methanol, although the CO conversion itself is low. Rhodium, as the intermediate situation between the Fischer-Tropsch metals and so-called methanosis metals, which provide the C2 useful C2 oxygenate, such as methanol, acetaldehyde, and acetic acid in the CO hydrogenation. The interesting point that the rhodium metal is quite naive, which are strongly affected by the metal additives or supporting metal oxides. In fact, the pressurized CO hydrogenation under the 21 bar and at the temperature 250, you can see in this figure the addition of iron to the rhodium enormously enhances the CO conversion by a factor of 10 to 100 times compared with rhodium itself, but keeping the C2 oxygenate and higher selectivity to hydrocarbons. But the other class of iron iron, the much suppress of the hydrocarbon formation, such as methane, and much improved of the oxygenate selectivity consisting of methanol and ethanol. The success preparation of the three composite catalysts consists of rhodium and two different types of the promoter, titanium ions, three composite catalysts provide the high selectivity for ethanol and high yield of oxygenates. So challenging subjects, how to understand the kind of the metal additives promote of the or the change of the oxygenate selectivity in the CO hydrogenation. Number of the work have been done to what kind of metal additives promote or the CO hydrogenation by changing the metal additives. And at moments, I would like to classify two major promotion role of the metal additives. One is that the early transition metals, such as manganese and zirconium, are much more oriented for the enhance of the activity due to the increase the CO dissociation. In contrast, the other class of metal groups, such as iron, zinc, molybdenum, the promote of the oxygenate, mostly alcohol, this enhanced selectivities. It is, at this keynote lecture, I'm much concerned iron in its nature for the CO hydrogenation. We easily say the ions enhance the CO dissociation and making the hydrocarbons. But as I told you, that the iron, if you combine with the noble metals, iron it loses their original natures. Rather suppress all the hydrocarbon production, rather improve all the alcohol production. So maybe iron itself, that's the electric space or some chemical properties, so much difference in combination of the noble metals. I will show you some interesting example to understand the promotion goals of these metal additives in the elementary processes of the CO hydrogenation. This is the CO-TPR profiles conducted by the flushing the hydrogen on the catalyst after conducted to the carbon monoxide. Here is the same peak monitored by the mass spectroscopy. It around 195 degrees C, and reduction of the surface oxygen to make the water is come out to the 90 degrees C on the nodule surface. But by the addition of the high transition metal manganese palladium, the kind of the same peak is shifted to lower temperatures, but the surface oxygen reduction peak is somehow shifted to higher temperature. Anyhow, this is a good example how this manganese palladium is active to promote the CO dissociation. But iron, what it is, exhibits a different trends for the promote of this or suppress of the CO activation. By addition of iron, showing this, that the methane peak is little bit higher temperatures. In contrast, is the reaction of oxygen, surface oxygen, shifting lower temperatures. The much more facilities on the ion from on the surface. Again, the zinc is much appreciation for the suppression of the CO dissociation. So one can usually expect this kind of the metal ion would be modified on the chlorine surface. This is also some clear evidence how this suppress the CO dissociation on the ion or the zinc modified chlorine surface. This IR spectrum show all the distinct sharp bands and broad breaking bands come up to 50, 58, and 80, 40 respectively. By additional ion, sorry, 1980, that by additional the ion, that the major difference is due to that kind of breathing carbonyl, much suppress and eventually disappear, particularly in the case of the zinc, very sensitive suppression by the addition of this ion. But the linear carbonyl, although they are a little bit broadened, but its intensity itself remains unchanged. So we speculate, or we propose idea, this kind of ion ring reside on the rhodium surface might be mostly at the from rich side and at the shallow position of the rhodium and present of the multi-breathing carbonyl, but not much for the linear carbonyl. We characterize that the kind of ion promotion promoted rhodium surface by means of the different technique, including exact, dense method, to understand the location of the promoted ion and the oxidation states after the hydrogen reaction or under the CS reaction, yes, zero hydrogenation. And eventually we propose the idea for the ion is so much concentrated, enriched on the surface layer of the rhodium particles. It is consistent with the data in the exact evaluation. From the MESPA data, we understand most of the iron it exists in the high association state of iron, although that the catalyst is reduced with the hydrogen at a high temperatures. After the hydrogen reduction, the some part of the iron, 25% or so, it completely reduce iron zero states. From the result data, nothing contribution ion bond, much major one for the rhodium ion. But ion is highly dispersed or isolated in forming rhodium ion alloy. Moreover, this ion type it is concentrates at the interface between rhodium and metal oxide supports. It is an interesting issue on the discussion of the ion addition. Ion is not that isolated. Most of the ion is in the vicinity of rhodium particle, although the silica support surface area quite large compared with the rhodium particle surface. So we are some driving force why these ions so much concentrated at the vicinity of rhodium particle. So we again try to discuss on the points what the counteractive side to address all the promotion of the iron to improve the oxygen production. So obviously we have the two different active sites consisting of the rhodium, reduced rhodium, and iron cation that adjacent two-side structure. And reduced iron and rhodium, reduced rhodium in forming alloy is another issue. So we try to use all the more well-characterized the active sites generated by the molecular precursors consisting of rhodium ions or some other combination of noble metals such as palladium ion, iridium ion. The carbonyl cluster having either well-defined metal network and well-defined metal composition. We have simply applied the conventional technique to eliminate of this kind of precursor compounds, include on the silica gel and along with the oxidation and the reduction. At the moment, I would like to simply show you of the very much good promotion of the iron in the case of the iron rhodium bimetal cluster as a precursor. This is a product distribution in the CO hydrogenation at low pressure, 5 bar, and the temperature 250 degrees C. Under the condition, rhodium cluster derived ones simply highly dispersed rhodium clean surface provide mostly the same. With a poor selectivity toward acetaldehyde, nothing for alcohol. Iron, if you use iron carbonyls as precursor, the resulting silica-supported material, nothing happens under CO hydrogenation. But very interesting, only iron two metals involving the rhodium cluster that the resulting material very much effective for production ethanol and methanol, and much suppressed for the hydrocarbon production. We appreciate the adjacent iron rhodium site would be derived from this kind of precursor molecule. It is responsible for the oxygen production. Some poor conventional chemistry for making the rhodium ion catalyst provided not much more they can do. Money due to the small contribution of rhodium ionization situation. So we try to characterize this kind of catalyst derived from the molecular carbonyl cluster. We have this, we showed of this some example for the exact evaluation on the rhodium ion coordination circumstance in terms of the position number and atom distances. Only I added some interesting edits we have created having a great contribution of rhodium ion or palladium ion compared with the rhodium. And we have a large number of contribution of ion oxygen bonds. We easily understand the classified catalyst, giving is a highly dispersed small metal particles consisting well characterized composition. And similar studies also again that the kind of feature of iron exists, whether the highest oxidation state of iron is plus, otherwise is the iron zero metal state. We have nothing contribution of the intermediate oxidation state of iron 1 plus or iron 2 plus in terms of the azimuth and couple in the necessary parameters. So we some ideas for this rhodium iron carbonate crust. If put onto the silica surface, it is easy eliminate CO to engrafted on the silica surface. Its iron is much very trivial for this attached to the oxygen on the support. And also it is how there's a very decent interaction with the rhodium small transfers. This kind of the situation is quite effective for the CO insertion activity judged by the olefin hydrogenation. It is a common processes, elemental process for the oxygen production in the CO hydrogenation. We admit the mixture of gas of propane and carbon monoxide and hydrogen onto the catalyst prepared from the different precursors consisting rhodium, iron, rhodium, or otherwise iron itself. That's much more higher promotion of the CO insertion to make the oxygenates butanol or the butyl aldehyde is obtained by the iron-containing rhodium cluster. By increasing the iron content, increasing the promotion of the CO insertion activity. But it's a very important point that the only one iron involving the rhodium cluster is a tremendous enhance of this oxygen production compared to rhodium itself. So this kind of the promotion is quite essential for this situation of iron loss. If you prepare the physical mixture, the catalyst by the physical mixture of rhodium and iron carbonates, you have not so much good promotion of this oxygen production. So again, the kind of the cartoon say rhodium iron should be decided and received, which gives it a good promotion for the oxygen. If you existing isolated each other, they give nothing more. Only these quite simple additive laws of forces. As I already Professor critical to introduce some idea to understand promotion role of the metal cation exists in the vicinity of the metal carbonate sites. This is the organometallic model compounds forming in the 1,2 adapt between the iron carbonate and this acid aluminum bromide. So to be it is a severe situation for this iron beside the reciprocal proton. It is quite specific and very interesting point. In the bridging carbonyls, having these large electron density on the oxygen end, it is much strongly interacted with the oxygen division size. And to give it your lower frequency carbonyl bands around 1600 orders. So, and also in the linear series, shifted high frequency. This kind of the interesting lower bands is observed, not so much, but others catalysts of this ion loading were ion under the export of carbon monoxide. It is similar to the observation of another combination of the bimetal catalyst. This situation is the same in this kind of organometal chemistry. It is from the manganese methyl carbonyl to mode is a kind of the reaction intermediate for the acyl as an intermediate of the oxygen production. And now they enhance, but factor 10 times 6 or 10 times 8. In addition of the precise reagents. So we, at the moment, to propose the kind of the heterometal sites consisting of one metal, usually another metal, oxidized ion, promote a zero insertion, migrated insertion reciprocal onto the carbonyl, making this two site activated acyl or the two site activated polymer, which is hydrogenated to give the ethanol or the methanol. And there's some idea of the mechanism of the isotopic kingdom as proposed by the Professor Sahara and I, based previously, consisting of the several different elementary steps, which require the different ensemble of the metal sites to promote each respectively. Ion promotion role will be addressed on the one is in the CO dissociation, suppressed by the breaking of the rhodium ensemble sites, informing the alloy. Others, it is a promotion much more specific for the CO insertion to make higher options. That's kind of the common promotion is applied for the current population. Recently, we have interesting result. It could be explained. It is the contribution of the two-site activation of CO. It's exactly involving the oxygen production. I'll give you, it is the result of the promotion of the oxygen alcohol production on the ruthenium cobalt bimetal clusters. There are the catalysts compared with ruthenium itself or cobalt itself. From the product distribution and low pressure syngas reaction, in the presence of the JSN combination of the cobalt and ruthenium, precursor, they give these higher yields of alcohol, methanol, ethanol, propanol, butanol, tritanol. But ruthenium carbonyl, if you use that precursor, you give a lot of hydrocarbon, nothing for oxygen. Cobalt is somehow gives a small amount of oxygen, but much more higher hydrocarbons. So again, we would like to address what the surface species form on the surface on this ruthenium cobalt JSN structure. This is the FTIR in situ, or this is a CO hydrogen absorption at around the room temperature onto the cobalt ruthenium carbonyl intermediate material compared with ruthenium 6 carbonyl. After the hydrogen reduction, we export the material to carbon monoxide. We get off the carbonyl bands attached on the ruthenium on the cobalt ruthenium, but the interesting bands appearing in 1680. Only observed on the cobalt ruthenium carbonyl cluster diagrams, but nothing on the ruthenium carbonyl diagrams. These particular bands appear in 1680 very number under the excluded carbon monoxide, switch with carbon 13 carbon monoxide. This band shift to low frequencies around 40 very numbers due to the isotopic shift of the carbon monoxide. So we try to discuss on this kind of particular band might be associated with this two-side activation between the ruthenium and cobalt. In the present time, if you export to this resorting material after the CO comes off, this particular bands at the 1680 level number, 1580, under the exposure of hydrogen at the 100 C. If you use the deuterium instead of the hydrogen, you get all this similar kind of the P around 50-75 level number. Is a little bit the flavor of the isotopic shift due to the hydrogen and deuterium. So we propose that kind of reaction. It is the two-side aqueous CO is converted into this formula-like intermediates by the attachment of this hydrogen, giving the particular carbonyl band at the 1580. In the literature, we have some interesting evidence to show all the higher bands associated formulas contained on the surface, not only of the organometal chemistry, but also other science, to show what the bands of the carbonyl or the formula is ranging around 1600 to 1550. Particularly interest for the figures reported by the doctor that it is a kind of either two-side CO accommodation of the formula or acetate. giving it a significant rate. So I would like to have a comment from this all people, how this kind of this judgment of this the assignment of the kids. Anyway, we have some interesting correlation between this particular bands around the 1580 on the surface derived from the cobalt selenium, which is quite effective for the alcohol production by the changing of the selenium cobalt composition. Against this, if you use of carbon surface steel, it is done with segment here. So it is area species is quite right for this based on the carbon monoxide. There's some right correlation between the oxygenate, the alcohol production yields against the peak intensities of the particular bands around 1584. Might be associated with a two-side activated formula. Higher concentration of these species, it is a quite parallel trend for the alcohol production on the different the selenium cobalt plus the catalyst. We have some interesting result. If you expose the hydrogen or deuterium onto the surface after the making of this kind of intermediate, you get out this methane and methanol rather than the deuterium monitored by mass. So we would like to say this kind of two-side species would be converted in the methanol was dissociated into the methane. So I will only a final OHBCs to show all the how to change all the surface species under the prolonged reaction of carbon monoxide hydrogen onto the selenium cobalt bimetal cluster catalyst. Increasing this the particular surface intermediates. At the same time, somehow the increasing the low temperature might be both by the hydrogen carbonate or the formates or the methoxy or the alkoxy intermediates. Again, we have some contribution of the product of higher alcohols in that sense. Now, it is, I wanted to show this, that the two-side CO activation might be involving the oxygen production on the selenium cobalt or rhodium ion bimetal side. Thanks for the contribution of the collaborators. I show you this. Thank you for your attention.
So the paper of Professor Ichikawa is open for the discussion.
I have two questions. The first one is I was a little bit surprised in the second transparency that you proposed. You gave a very good selectivity, it seems that 50 for oxygenate for a rhodium deposited on silica. And some author said that rhodium deposited on silica gave only hydrocarbon formation. Could you comment?
Pressure effect is very quite significant to discuss on the oxygen production on the rhodium catalyst.
The rhodium deposited on silica.
Yes. So that the lower pressure,
No,
CO hydrogenation, we have the lots of the same. It's under the carbon monoxide, strongly attached on the volume, is giving you some amount of the oxygenate, but conversion is quite low volume step.
Is it not a problem of the silica protein as indicated by Vladimir Pomech?
So no.
Can you comment on the state of dispersion of your catalyst? There must be some sintering going on.
Yeah. Are you talking about the cluster?
Yeah.
Yes. Unavoidably, see the some clusters is highly dispersed, so it's a little bit easy to migrate to happen to synthesize under the prevailing reaction condition. But fortunately, is the iron-containing cluster or the cobalt-containing cluster, it is quite stable. Not so much the decline of the initial activity. So maybe iron with this higher oxidation state acting as an anchor of the volume or the palladium particle to presence. But really, it is unavoidably, slowly.
But do you think you have mostly just the isolated cluster with no
from this
polymerization?
yes, examples and hydrogenation transmission microscope, the studies, we understand in the size of the particles is arranged around the 10 or 15 angstrom. Might be 2 ST clusters aggregate and attached on the surface.
During your field experiments, do you have any evidence of the formation of a band at 28 wave number due to Formil species?
28
number. The Formil species should absorb this low frequency of the station 28 number per number.
It's hard to say.
28 or maybe
2800.
It is deuterium explosive.
80.
Is this deuterium hydroxide might be? It's not.
The problem is about the Formil species. The problem is about the Formil species.
Yes, that's kind of the formula species.
Yes.
Yeah.
Might be associated with the CH bond.
Yes. Do you have any evidence of that?
But if you switch the deuterium, that's kind of shifted to 24 or 2600 wave now. I'm not sure, but so that is a might be CH bond and associated with the formula.
Please.
So we have again stressed this organometallic aspect, which seems to enhance insertion rates. Now, if I understand right, you have again seen the C and O bonded species. You probably have also seen some evidence for the importance of the species for the formule formation. But how about the insertion? I did not see any new argument which really, from an experimental point of view, supports the enhanced rate of insertion. Did I understand you right, or did I miss a point?
No, I agree with you that the kind of the analogy of the organometal chemistry we discussed on the promotion law of the with acid reagents. They say it's not to claim on the catalytic process, only the elementary process from the migration, necessary migration onto the carbonate. It is enormously enhanced by the informing of the adapt. But the catalytic process could be a little bit behind of the something if it is very stable adapt complex in the intermediate form, maybe that reactions cannot proceed. So that is, I would like to address it as a kind of not so strong interaction with this carbonyl could be a much more pronounced of the CO insertion.
No, but my question is, do you have any additional experimental evidence that this CNO-bonded species is really an intermediate? Does it participate in the reaction, or is it just a spectator?
Well, we have some supporting those evidence, only some kind of this formation of the adjacent structure of its importance for the promotion role of the oxygenates. One. And other is, as I told you, in the case of the ruthenium cobalt, it is almost low frequency species, obviously associated with two-side activation funds, could be converted into the formula. I claim, but many arguments here, but yes, there is eventually converted into methanol or just higher hydrocarbons. So I might say in the case of the ruthenium cobalt, might be a two-side active species involving the oxygen.
So I beg your pardon. Many people have asked to make some questions. I propose a short section during the coffee break. And many people are interested to discuss with Professor Ichikawa, also myself. So please, at the coffee break, we will join all together and we will continue this discussion. Thank you. Please.